So let's start the class. I will try to give clues about homework, the class before, just to give you some motivation to come, right? So we're going to have a assignment maybe for next week, Wednesday. So on Monday, I will give you some answers, right? Where did we stop? So we talked, so this is the first unit. Before that, it was just an introduction, and we are talking about the scales in the universe in terms of distances. So this is my favorite place in the world, right? Italia. So you start here 100 meter per 100 meter. That's San Marco. And then you zoom out. Then you have Venice and the island here. And then you keep zooming out, right? So we did that last time. So I just want to define here 1 AU. Okay, is the distance, because then it becomes too big. 150 million kilometer. We cannot even comprehend how big it is. So we defined a new unit here, 1 AU, which means astronomical unit. So that will be the distance between the Earth, which is here, and the Sun. Okay, yes. It's almost circular, which is not the case of Pluto, for example, which is an ellipse. But a circle is just a special case of a circle. So plus or minus is almost like a circle. So even at the time of Copernicus, they knew about the relative distances between the Earth and between the Sun and the planets. So for example, the Earth will be 1 AU. So based on that, Mars will be 1.5. Okay, so this is the Sun, this is the Earth. So 1.5 will be Mars. And then you see Jupiter is really far away. So 1, 2, 3, 4, 5 AU. And by at the time they only knew about Saturn, right? And they didn't know about the planets. And this is what we know today. So now we know the absolute values of those distances, and you see it was pretty close. So they are pretty good. Okay, so zooming out, you have 1 billion kilometer per 1 billion kilometer, and you're gonna have the solar system. Okay, so bless you. So I just want to show you a video to give you a better idea. This is so I don't know if we have a good resolution with that projector. If we don't, you can look here on that screen.
Since the Big Bang, the universe has continued to grow and expand. To understand just how big it has grown, we need to take an imaginary spaceship ride from the Earth to the edge of the possible universe. Our nearest neighbor is the Moon, just 250,000 miles away. At the center of our solar system, 93 million miles away, is our Sun. In the center of our solar system, we continue our flight beyond the orbit of the Earth. The next planet out is Mars. Beyond the orbit of Mars is the asteroid belt.
So here you have a better resolution. No, the resolution here is not very good.
1 billion miles away is the giant outer planet Saturn, almost 1,000 times the size of Earth. As we leave the solar system, we would pass one of our earliest interplanetary explorers, Voyager 1, launched in 1977 and traveling at a mere 40,000 miles per hour. Proxima Centauri and Alpha Centauri, A and B, our nearest stars, 25 million miles away. Our solar system sits in the quiet suburbs of a spiral galaxy, the Milky Way.
You can look here in this screen.
Every star we can see in the night sky lies within our own galaxy. This is deep space. Out beyond the Milky Way, 10 million miles from Earth, is the next spiral galaxy, Andromeda. Even traveling at the speed of light, it will take 2 million years to reach here. Andromeda and the Milky Way form part of a small cluster of galaxies called the Local Group. But stretching out way beyond the Local Group are much greater clusters of galaxies. If it were possible to travel fast enough for long enough and reach the edge of the known universe, this is what we would see. Uneven clusters of galaxies, a pattern that was predetermined from the very first second of the Big Bang. This is as far as our spaceship can take us. We are now 50 billion trillion miles from Earth. This is where science ends and speculation begins. Astronomers may never see what lies beyond here. This is where the secrets of the universe are hidden.
So it's a very nice video. I need to clean the lens. I think the resolution is not very good, but you have this screen here. Hopefully you can look at this. And then I have another one, which is very nice, which is, let's see, scale. Is that this one? So it's Venice again. See Venice? This is Venice. You see the canal here? That's the track. Or you have a train taking you there. You can also drive. And this is, I forgot. It's like a monastery, a very famous monastery over there from Armenian monastery. And so anyway, let's go back to astronomy. So you're zooming out. So that will be the Earth, 10,000 kilometer wide. You zoom out, zoom out, zoom out. And again, when it's dark, there is not a good resolution. So you might want to look at the screen here. You can move if you want. So there is nothing but stars, right? Zooming out, zooming out. Okay, so that's the Milky Way. You have a super black hole here, supermassive black hole. You have tiny galaxies orbiting our galaxy. They are called dwarf galaxies. And then you have clusters, groups of galaxies, and then you have the entire universe that looks like a cosmic web if you zoom out enough. And some people have noticed that cosmic web very much looks like your brain. If you look at the brain, the connections between neurons, so that will be a very small scale, looks like this very large scale, cosmic waves. It's like a filament, right? It's like a network. So instead of having neurons, you have clusters of galaxies. Okay, see, if you zoom, this is not science fiction, right? It's based on collecting data all around us. That's what, if you zoom out enough, that's what you will see. It's really like a web, a network, right? And along those filaments, you have dark matter, okay, which is 25% of the universe, gluing those clusters together. In between, you have void with nothing, just fabric that will expand. But the filament, they cannot expand because they are glued together. I mean, the galaxies, the groups of galaxies are glued together. Yes.
I saw something online that suggests, to remind me of it, talk about the density of the universe and the density of galaxies. It suggested that when the Milky Way collides with Andromeda, that there's such low density in both galaxies that there won't be any actual collisions or very few. Is that
Yeah.
true? Or?
No, that's true that there is so much void between the group of stars that they are supposed to pass each other, but maybe the dark matter will collide with each other. Right? But we will get back to that. But it's true. It will be passing us. Because you have a lot of void between the stars. Okay, and then so we can talk also of scales when it comes to the size of the planets. So this one is the largest planet, that will be Jupiter. And then you have Saturn, Uranus, and then Neptune. And then here you have the Earth. Okay, so the Earth in size, if you take the ratio, is about 10 times smaller than Jupiter. So you could put 10 Earth across it. Okay, so then you have Mars here, Venus is like the same size as the Earth, and then Mercury here, and here you have the moon of Mars, the moon of the Earth. Okay, these are the 4 moons of Jupiter that was observed for the first time by Galileo, right? The 4 moons, the main moons, and then you have many, 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 many moons. And then here it's Pluto, because that was before its demotion, right? It was demoted in 2006. Before that, it used to be a planet with its own moon. Okay, so just to give you an idea of the scale. And then if you want to include the sun as well, it's going to be something like this, right? We have to compare, because if I just give you the distance in kilometers or in AU, it's hard to imagine. But if you compare, if you take the relative distances, so then you make sense of it, right? So that will be our sun, which is an average star, not that big, just average, just medium. And you see Jupiter is here. You can put 10 Jupiters across the sun. And then you have Saturn over there, and you have the other planets here, including the Earth, which is, I don't know which one is this. It should be that one here. It's very small. Okay. And then that will be Centaurus. So it's a constellation. So I told you that sometimes, the constellations, they don't make sense. It's very hard to see, for example, a bear, if you look at the big bear. But in that case, you can see it, right? What it looks like. Like, if you know what a centaur is, you can see this is half man and half horse. So this is called Centaurus. So most of the centaur were very, very mean. especially toward the human, except one that I forgot the name. He's the one who trained Hercules, if you have seen the cartoon, for example. So there was only one who was like well-minded. The other one had a lot of mischief, right? So this is called Centaurus. You cannot see it in the northern hemisphere. It's only in the southern hemisphere. In the south hemisphere, you can see Centaurus. And here, that will show you the South Pole. So in the north, we have Polaris, the North Pole. So you have the axis of the Earth, and it's pointing to Polaris in the north, and in the south, it's pointing to the cross here. So there is no star here, just a cross that says here the south. Right? Southern hemisphere, the axis will aim at that cross here. So anyway, that constellation here, you're going to find a system of 3 stars, and one of them is called Proxima Centauri. Proxima means proximity, so it's the closest star from our sun. It's its closest neighbor, Proxima Centauri, and it's a distance of about 4 light years away, which means we see Proxima Centauri as it was 4 years ago. So if it was to disappear for some strange reason, then we will not know it before 4 years passed. Okay, so again, 4 light years, which means 1 light year is a distance of 6 trillion miles. 6 trillion miles. So it's really big distance. So I don't know if I have a picture of Proxima Centauri. Peep here. So here you have the size of our sun, and these are the 3 stars that make up that Proxima Centauri system, okay, including this one. So it's very small. It's a red dwarf. It's a very small star, very greedy. So we're going to see that the red star, they have a very slow metabolism. So they're going to burn their fuel very, very slowly, right? And this is our sun, which is average. It will last for another about 4 billion years. We still have time. Picture Centaurus. Let's see if I have a picture of Centaurus here. So you have the northern hemisphere. You see Cassiopeia here, and then you have the little bear, which is the little deeper, and then you have the big one here. Now here is the southern hemisphere, and you have the Centaurus here, and the northern cross is here, right? Okay, so zooming out again, the Milky Way is about 100,000 light years across. So if you live there and you send a message to your friend, like a radio signal, because nothing can go faster than the speed of light. So the best you can do is to use a radio signal, for example. Then it will take 100,000 years for your friend to get it, and another 100,000 years for you to get his message back. So these are crazy distance, right? And the sun, and it's spinning, the Milky Way is spinning, and the sun, with all its planets, is going around that Milky Way. So it's flat, it's a disk, and we know now that you have a supermassive black hole at the center. And recently, like a few years ago, they took a picture of that black hole. It was not the first one, right? We talked about that last time. I think it's in the assignment. But they took a picture of a black hole in one galaxy named M87. Okay, we already talked about that. I'm not going to go back. So that will be the Milky Way. Now you zoom out even more, and now you have the local group. So it's our neighborhood. Okay, so it's a group of galaxies, and it's called the local group. Okay, so that will be a question on the pop quiz. So if you want to go from small to big, you go from the the solar system, then you go to the Milky Way, then you go to the local group, then you go to the Virgo supercluster, and then you go to the universe. So this is our local group, and the biggest galaxy here is Andromeda. So it's a giant galaxy, and as he said, they are coming toward each other, and they are supposed to collide with each other. But because you have so much void between the stars, they are supposed to pass each other. Right? So it's 2.5 million light years away. And then we have like very cute galaxies. Here they are called dwarf galaxies, and dwarf not as a noun but as an adjective. So it's not like the dwarf planet that was very insulting for Pluto, because dwarf as a noun, so not only it's not a planet anymore, but it's a dwarf. Right. So anyway, you have the small Magellanic Cloud and the large Magellanic Cloud, which are tiny little galaxies orbiting. It's like a moon, right? They orbit our own galaxy. So everything here is very dynamic. It's always moving all the time. So this is called the local group. Okay, so the local group is part of a group of galaxies, which is called the Virgo supercluster. So it's a group of galaxies. From our perspective, it seems that we are at the center of that Virgo supercluster, but it's just relative to us. At the center, really, you have the Virgo cluster, and at the center of the Virgo cluster, you have an interesting galaxy here, which is called the M87. It's a monster. It fed on other galaxies, right? It was eating other galaxies, so it became huge. And at the center, you have this very famous black hole that made the news, because this is the first black hole we took a picture of before our own black hole, because we didn't have the right resolution yet. So it was easier to take a picture of a black hole in another galaxy, in another cluster of galaxies, right? So how big that is? 60 million light years. So if you are here, you want to talk to your friend, it will take 60 million years for him to get the message. So 2017, so it's not long ago, right? The first picture of a black hole by a telescope, which is called a radio telescope. So a telescope, remember, it's just a big dish where you collect light from the universe and then you analyze that light. So bigger the telescope is, more resolution you will get. So resolution is how well you can tell you can tell 2 points apart, right? So if I take two of you and I move you very far away, I will even know that you are two. It will merge in one. So that will be the resolution. You know how far I can place you. So with my eyes, I see two before I can see only one. So with a very good resolution, meaning with a very, 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 very big dish, then you can take a picture of a black hole. So you can search Event Horizon Telescope, because actually it's not really a telescope, it's a network of radio telescopes placed all over the planet, and everything happens like you have an Earth, the size of the Earth telescope. So that was a big breakthrough. So that will be the local group. Okay, so this is called, it's a nice picture. So our place in the universe, the Earth belongs to the solar system. Here, that will be the orbit of Pluto. So you see it's describing an ellipse. That belongs to the solar system as you zoom out. Okay, so it's not just the planets, but the solar system includes what we call here the Kuiper belt. So all kind of junks orbiting the sun. And then here you have another part which is called the Oort cloud, other junks orbiting the sun, because gravity is a force infinite. Right? It can grab something from at a very, very large distance. Then our sun belongs to the neighborhood, including Proxima Centauri. That belongs to the Milky Way. That belongs to the local group, 50 galaxies glued together, including Andromeda Galaxy. That belongs to the Virgo supercluster, with the Virgo cluster at the center where the black hole is. And then that belongs to another structure. Okay, so I think I told you, so that will be slide. Okay, last time, okay, let's see. So, and recently, okay, that was in the news. We talked about that last time, but recently they found a new structure. A new structure we belong to, which is called, I have to say it right, Laniakea. Okay, so this is Laniakea here, and the Virgo cluster is over there where we belong to. And this is a huge structure. Okay, so it's made of dark matter, and you have all those group of galaxies glued together. And here you have something very strange called the Great Attractor. I can see that. I can see how we could make a great movie called The Great Attractor. It's an amazing title for a movie. So anyway, yeah, you have something there, and they don't really understand what's going on, that will pull everything toward it, right? So even though the universe is expanding, accelerating, but along the filament here, it can be pulled in. Isn't that interesting? Okay, so this is the Virgo supercluster, where the Virgo cluster belongs to, and the local group. So I don't know if I have a picture of the Virgo. So this is the Virgo supercluster. At the center, you have the Virgo cluster with that famous black hole. And we are somewhere over here, the local group, but our group is so tiny because it's only 50 galaxies that it doesn't show. But we are about here, south, down to the right, so we are somewhere there. So there is a lot of very weird things in astronomy now. Okay, so I found this video, so I hope I won't be in trouble with the copyright. Sometimes I am.
Somewhere in the universe, small blue planet. The third rock in the star called the Sun. Just one of billions of stars in a spiral galaxy known as the Milky Way. But where in the universe is the Milky Way? A team of scientists gathered data on more than 8,000 of the galaxies that surround us. They mapped each galaxy's position and movement in space. And, for the first time, they've shown that the Milky Way is part of a much larger system of galaxies, a supercluster that they have named Laniakea. The Milky Way is nested in the furthest reaches of this structure, on the outskirts. The entire universe can be seen as an intricate network of galaxies, a cosmic web. Some areas are almost empty, dark voids. Others are densely packed with galaxies in regions known as superclusters. Superclusters are the biggest structures found in the universe, but scientists have struggled to define where one ends and another begins. To map our home supercluster, a team led by Brent Tully at the University of Hawaii studied the motions of the galaxies around us in unprecedented detail. Even though the entire universe is expanding rapidly, gravity is also at work, pulling against this acceleration. By discounting cosmic expansion, the team worked out which galaxies are being pulled towards us, shown in blue, and which are being pulled away.
So what you see a void here, it doesn't mean it's really a void, it's just that they just survey only that part of the universe, right? So that's why you have data missing. It's not that it's not there, it's there, but we didn't take a survey of that.
In red. This enabled them to create a map of cosmic flows, the paths that galaxies migrate along, tugged at a tiny pace by the force of gravity. Using this motion, they came up with a new way to map the distribution of matter in the universe. Delving into our home supercluster, you can see that most galaxies are being pulled towards a dense centre. This is known as the Great Attractor. Our galaxy is among those sliding towards this patch of space, which dominates our region of the universe. Let's take a different view. Each circle represents a galaxy. Again, you can see most galaxies being pulled towards the Great Attractor in the direction of the arrows. Between the Great Attractor and us, the Milky Way, there's a relatively empty area, a blue void. And next to us is Virgo, a large and dense cluster whose bright galaxies have been observed from Earth for centuries. Until now, astronomers grouped us, the Milky Way and its surrounding galaxies, with Virgo and nearly 100 other clusters in a supercluster that stretches 100 million light-years across. But using this new technique, we can see that this is just the tip of the iceberg. This cluster of clusters is...
So you see, that was the Virgo supercluster, and my slides used to stop here. But now they have increased the last structure.
Maybe an appendage of a much larger supercluster, more than 100 times bigger and more massive. But how did the team know how to redraw the boundaries of this cosmic map? Here's our supercluster in black, and a neighbouring structure, Perseus Pisces, in red. Scientists define the boundary as the points where the flows of galaxies diverge, like water dividing at a watershed. This is where neighbouring structures shear apart. This is the first clear definition of a supercluster. Laniakea means immeasurable heaven in Hawaiian, a fitting name for the vast community of galaxies that we are a part of. So now we know that on the edge of a supercluster called Laniakea, in a galaxy called the Milky Way, around a star called the Sun, there is a small blue planet, our home.
It's a very nice video. So they are trying to redefine the structure here, right? And the Laniakea, so it's something new. It's very strange. Okay, and then you can zoom out even more. So then you have 100 million light years until you reach the age of the universe, which we don't know what happens after that. But as I told you, if you zoom out enough, then you see this web that looks like neuron connection. You know, in the brain, you have neurons talking to each other, right? And it looks exactly the same. So it seems like something, who was in charge of making the universe wanted to be as efficient as possible. So use the same template for the very big and for the very small. Okay, so if you zoom out enough, so that's a picture, it's a real picture that we took of the universe just after the Big Bang, because we cannot look into the Big Bang, because the only thing you can look into something is to collect light. So during the Big Bang, light was not able to escape. The photons, right? They were reabsorb, re-emit. So we don't know what was going on. But just after that, when the universe started to cool down, then the light will escape. And if we look very far away, then 400,000 years just after the Big Bang, that's the picture that we get of the universe. So what you see here, it's like hot spots. Okay, so these are the future group or clusters of galaxies in the making, and you see the void. And interesting enough, you see that it's homogeneous all over. So it looks the same, doesn't matter which way you look, the universe looks the same. And they think this is because the Big Bang happened like so quickly, okay, exponentially expanding, that the part of the universe here didn't have time to differentiate from this part. Okay, so we have that picture here. I have a very nice video about that. It's from the book I recommend for this class. No, maybe not. Maybe this one is another one. No, that's not the one. Okay, that's from the book I recommend.
Yeah. Picture of the universe nicely shows that, where you have small, hot, and cold spots. Well, they look small here, but these are actually the seeds from which giant superclusters of galaxies form, and the voids between them. And maybe the very smallest ones correspond to what we now observe as big individual clusters at best, but most of them are superclusters and giant voids. And you can do numerical simulations of the collapse of material from these initial fluctuations going over the course of 13 billion years, as shown at the lower left there. That's the time in billions of years ago. You can see material collapsing.
And again, you have better resolution here.
Clusters and superclusters. In between them, there are voids. And the actual observations of the real distribution of galaxies and clusters in the universe resembles in close detail what we get from these massive numerical computations with supercomputers and with many computers linked together. Here we see things from different perspectives because they've artificially rotated the whole universe, but really we don't think the universe itself is rotating. The sixth big success of the Big Bang Theory is that the observed abundance of helium you map picture.
Okay, so that is you have a series of classes, like could be history, sociology, whatever you're into it. It's called Great Course, right? It's online. And one of these class is taught by this professor, and it's called, I don't know what it's called, Introduction to Astronomy or something like this. So very interesting, but it's based on the book, the textbook. Okay, another thing I wanted to show you is non-universe. This is also a very nice video. So it's the Museum of Natural History in New York City. And I don't know, again, the better resolution is here. So you start from the Himalayas, right? India and China. So they zoom out. Zooming out. So again, 10,000 kilometers wide. See India, China, Himalayas. Maybe I'm going to speed up a little bit. So all the junks, this is all the junks we put around the Earth, all the satellites, even some of them, many of them are not even working. You just chill out. More junks. So 1 second for light, you have the moon orbit. And again, you can watch that screen. And you have the planets. And they tell you here the time it takes for light to travel. You have the zodiac constellation. You see here the teapot. This is the teapot. This is the scorpion, Scorpius. $70 for light to travel. So we have the Milky Way. 100,000 years to go from one end to the other one. So this is the same image you saw before. So it doesn't mean that there's a giant butterfly. It just means that and this were not surveyed. $5 billion. So quasars are the early galaxies just after the Big Bang. And this is the baby universe. And after that, there is a red tape that says can't, don't know. And we go back. Let's go back faster. Okay, so you get the point. I have 2 more videos just to give you an idea of the size, scale. So each time I see something on Twitter, on X, I grab and I download because you can find really cool things. Yes, Canvas. Yes, I have uploaded the videos on Canvas, right? Some of them. If you look in Canvas, the unit scale, you're gonna see them. But I'm recording anyway, so if you want to watch them again, it's in the video I'm recording on YouTube. Yes. Oh yes. So you're right. So in Canvas, in the unit about scales, you will find some videos I have uploaded. You're right. I forgot to mention that. So for each unit, you will find some links to videos I found interesting. So you can take your time. You are right. So Space Shuttle is retired, right? Phased out. I think you can visit it in New York City. But anyway, this is the astronaut. This is the Hubble Space Telescope. This is the Space Shuttle. So just to give you the size of handmade object. So that's an asteroid. That's the moon of Mars. Another asteroid looks like a potato. Asteroid Ceres. So Ceres here is a dwarf planet, like Pluto now. So it belongs to the Kuiper belt. No, what do I say? That rewind. I'm getting tired. Sorry. Forgot about what I said. It's an asteroid. No. I know why I say that. Okay. Rewind. Ceres here was the first asteroid discovered that belongs to the asteroid belt between Mars and Jupiter. So this one was the first one. So first, it got promoted. So it got planethood. So it was a planet, right? And then it was demoted to an asteroid. And then when Pluto was demoted, it was promoted to be a dwarf planet. Go figure, okay? So it started as a planet because it was spherical and it was the first asteroid we were ever seeing. And then it was demoted to an asteroid because we keep seeing more asteroids. And then when they decided to demote Pluto to a dwarf planet, it was promoted to dwarf planet. So it got a promotion. So this is another. So Pluto is a dwarf planet. That's a moon of Jupiter. Moon of the Earth. Io is a moon of Jupiter. Mercury is a planet. Mars. Sirius is the brightest star in the sky. You have Venus, you have the Earth. That's an exoplanet. So all the exoplanets, so some of them, they will start with Kepler. So it's another exoplanet here. It's a giant Earth. Neptune. Just to give you idea of the size, right? The Sun, Sirius A, Pollux. So this is here, what you see here, it's a black hole. Okay, it's the black hole at the center of our own galaxy. So remember we talked about Scorpius. So the tail of the Scorpius is showing you where the black hole is. Aldebaran Rigel is part of Orion constellation. Betelgeuse. Uiscuti, it has a very cute name. That's a black hole we took a picture of. Another black hole. Galaxy. Dark Nebula. Ring Nebula. Butterfly Nebula. Going even bigger. Tycho Supernova. So you see it's increasing in size. Cartwheel Galaxy, Andromeda Galaxy. So Virgo supercluster, Laniakea supercluster, and then the universe. Isn't that nice? Right? We go over again and again and again. So hopefully it will stay. I'm gonna go faster, okay? Pluto. Okay, let's go faster. Look at the sun. This is the sun. How small is the sun compared to those crazy stars? That's the black hole, Aldebaran. You don't even see the sun. That's a huge star. So it's called a hypergiant star. So huge. You is Scotty! But even bigger. That's a black hole. Another black hole. Sleeping Beauty, isn't that nice? Milky Way. And Laniakia. And then the whole universe. Okay. So scale in the universe, that's it. Okay, we are almost at the end of that unit. And you see the solar system, Milky Way, local group, and then the Virgo supercluster, Laniakia, and the visible universe. So we use to find distances. We don't use British units. So by the way, they were those units, feet and inch and yard and miles. That was developed by the British, but the British don't use them anymore. No one uses it in the world except us and another country that I forgot. But we all use metric system except us. I know. Maybe it will be too much money, to switch another system. But metric system, that's what they use to find the scales in the universe and AU and light years.
Reason we don't use metric system is because when they ordered the units to be brought to the United States in the 18th century, pirates plundered the ship and lost it to the sea.
Oh, okay. But by then, now they could switch to it. But that's interesting. So they used to have like sample to make sure what a meter was, and that was in France, right? But we are still using the British system. Okay, so a light year is a distance traveled in 1 year. It's about 6 trillion miles. 6 trillion miles. So it's a big, big distance. So, for example, how long does it take for light to reach us from the moon? 1 second. So that's why if you listen to the audio from when they were on the moon, they will say, "Hey, how are you?" And then nothing. And then they say, "Fine." Okay, because it takes time for signals to travel. So if you want to know the math, so I gave up. Okay, when I was teaching this class, I used to do some math, but I gave up on that. But if you are interested, you can see the math is pretty easy. Okay, you divide the distance by the speed. Okay, or enjoy the math here too. It's gonna give you all the steps. So Orion, 5 more minutes. Can you bear with me like 5 more minutes? Okay, thank you. So Orion, we see it as it was 1500 years ago. Okay, this is my favorite constellation. Alpha Centauri, part of the Centaurus constellation, is 4 light years away. You have the Andromeda, 2.5 million light years away. And this is one of the oldest galaxies, so it doesn't exist anymore. But when you look far, 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 far away, okay, at a distance 13.7 billion light years away. So that will be the age of the universe. That's a baby galaxy, one of the first galaxies. Okay, so at a greater distance, that means you go back in time. Okay, so the universe is about 14 years old. The Milky Way, 13. Solar system, 4.6. That's how old is our sun. And it has about 4.5 billion years to go. Okay, and then if you are in Earth science, you have some numbers as well. Okay, so this is the oldest fossilized. It's called stromatolites. Okay, trilobites. Okay, 500 million years there was an explosion of life on Earth. 65 million years, that was the death of the dinosaur. So if you take the age of the universe and you scale it down to just 1 year. So here you have January 1st, the Big Bang, okay, and the first galaxies, and then nothing, and then here you're gonna have the Earth, right, 4.5 billion years ago, and then nothing special, and a few seconds before midnight, that's when we come along, okay, so industrial revolution, like very, like 1 second ago. So we are like in the time scale, it's really 1 second ago that we have the civilization as we know now. So there is a music that I'm sure you know, that summarize everything. They go really fast, but it's a good summary.
Sleeping near me 14 years ago, stay sharp. And your trophy game again.
So actually, it's a real band. I forgot the names of this band, but they did also a song about the periodic table. So they are famous. I just forgot their name. So that's the song that this very famous series used, which I don't like too much because people think now that all physics professors are weirdos, which we are not. So now for next class, we're gonna start a new unit about history. Okay, so it will be called Unit 2, on the shoulders of giants. So we'll talk about Copernicus, Galileo, and Newton, and even modern history. Okay. So now we go to the pop